Hi, my name is Linn Emelie. I am a PhD student in Work Package 3, and my topic is on modeling of environmental constraints in hydropower scheduling models. And I'll present some of my ongoing work. I'm currently a bit more than a year into my PhD. So this is not done yet, it's work in progress. So first, quickly, why modeling of environmental constraints? Well, several Norwegian hydropower plants have imposed environmental constraints on the operations. And also, we're currently in a period of revision of license, so there might be changes in these constraints or there might be imposed new environmental constraints. So it's important to understand the impact of these type of constraints on the operations, on the reservoir management, and also just on the system as a whole. And some of these constraints are more complex than other constraints. So especially constraints that include logical conditions, if this then that, or state dependencies, they can be more challenging to include in the scheduling models that the producers use when planning how to operate the hydropower plants. So in work package 3, there is a project 3.4 that focuses on this, how to model these complex constraints in the scheduling problem. And there is also a hydrogen report that discusses this a bit more, and that's based on a survey where they have asked the hydropower producers what type of constraints that they find challenging to handle in operations. In my work, I've chosen to develop a model based on stochastic dynamic programming, which is not necessarily the same method that is used in the operational models of this type, but it's a method that allows for implementation of state-dependent constraints, and it's therefore very useful for my work. And maybe one of the most important things is that it's easier to handle nonlinearities and non-convex behavior in this method. And also when we have state-dependent logical conditions, we can handle some of these in the algorithm instead of the optimization problem. And state-dependent logical conditions, what's that? Well, it's we talk about the state of the system, the current state. So normal would be what's the reservoir filling level? So what's the reservoir level now or in this situation? And also what's the inflow scenario? And in the SDP method, we decompose a very large problem into several smaller problems that we solve, small optimization problems. And we, or among other things, we discretize the state space. So we have several discrete levels of reservoir filling and different scenarios of inflow, and we solve smaller optimization problems for each of these state nodes. And when we have state dependencies, implying that if, for example, the reservoir level is a certain level, or if the inflow is above a certain level or below a certain level, some kind of constraints become active or deactivated, we can check this in the algorithm and handle it in the algorithm instead of in the optimization problem, which is an advantage in this case. But of course, this method also has some weaknesses, so it's not well, since you have to discretize the state space, it becomes very quickly very big. So the problem becomes big and it's not that well suited to scale to large systems, but it's useful for smaller systems and for my research topic. And I especially focus on state-dependent discharge capacity. So that's basically a discharge limitation. You're not allowed to discharge from your reservoir. It could be a complete stop or to a predefined lower level, or even a state-dependent level, which in this case normally would be an inflow-dependent level. And this kind of constraint normally have a start criterion. It could be a certain date, or it could be dynamic, so it could be the end of the low inflow period, which you normally don't exactly know when it's going to happen during the year. Or it could be the sum inflow that you have kind of accumulated during the year. So normally this type of constraint will become active in the spring, but you don't necessarily know exactly when. And then it will be active until you reach a certain reservoir level. It could also be until a certain date, but normally it's what you want to achieve is that the reservoir level is, or the filling of the reservoir is above a certain level. And in my current work, I have implemented one version of this constraint, so it can come in kind of different flavors, this type of constraint. And the constraint I've implemented is one that is imposed on Hamlagrøvatnet in Bergsdalsvassdraget. It's in the west coast of Norway, close to Bergen. So I'm modeling the two upper reservoirs in this water course. And that's a discharge stop, except to fulfill minimum flow requirements. And it's activated by the end of the low inflow period. Or if it hasn't already been activated, it will also be activated by a certain date. So you can have early activation, or at some date you know that it will be activated no matter what. But this constraint, it has three different phases. So it's first a discharge stop, but then when or if you reach the wanted reservoir level, it turns into a minimum reservoir level requirement. We are not allowed to go back down under that level for a while until you come into phase 3, which is no decrease in reservoir level limitation, implying that you can, for a certain period of time, not accumulate water and use it above, like you have to use the inflow you have or save it until after a given date. So there are several things to handle in this kind of constraint. So I can understand that it's complex for the hydropower schedulers, planners to think about all of this. I've implemented it in a test model, and I wanted to show you some preliminary results. So this plot shows the production in the lower reservoir, and that's the reservoir that has this constraint imposed on it. And the upper plot is, maybe I can put this. This is without this type of, or this constraint implemented, while the lower plot is with the constraint, and this is the production from the reservoir. So this is very closely related to the discharge from the reservoir. And you can see when we have this environmental constraint imposed, there is a stop in production for a while. And we can, in some weeks here, there are for some, so these are results that are simulated for a lot of different scenarios of inflow. And you can see that there will be in some scenarios be an early activation, but by a certain date, this constraint is activated no matter what. And then it's activated for a long time, but if you reach the wanted reservoir level, you're allowed to start to produce some of your water. So moving over here, you have an increase in production again in some scenarios. Until in week 35, you're completely finished with all of these three phases in the restriction. So we clearly see a large impact. And if you look at the reservoir level or the filling degree in the reservoir, the upper is without the restriction and the lower is with. And you can see that we clearly see that the restriction has the wanted effect. You much more quickly fill up your reservoir and you have a higher reservoir filling for a longer period, which is why this constraint is imposed in the first place. But we also have some other interesting results. We're interested in looking at how these kind of constraints impact the water values. Then the water values are something you use to in the planning to understand if you should use your water now or save it for later. So it's a very important input to the model. And when we have these kind of constraints, we get a non-convex behavior in the future value evaluation. So this is two water value curves. And the upper one is without an environmental constraint. And the other one is with this type of environmental constraint. And it's 4 different filling degrees in the reservoir. And what we see is that we get this very funny change in value around. So this is also the reservoir level that you want to achieve in your reservoir. And this is the kind of behavior that we are interested in looking more into. So that's what I'm currently doing. I'm still verifying and testing to see if this is correct, and also what it really means. Why do we get this kind of behavior, and what does it mean for the hydropower scheduling and how we handle these type of constraints. So main takeaways: we can model these state-dependent constraints in SDP-based optimization models, and we see a large impact of these constraints on reservoir management. We also see very interesting impacts on the water value curves, also non-convex behavior, which could be a sign that we do need to improve the representation of these type of constraints in the operational models. At least it's very interesting to look further into.